All right, I believe we left off and didn't quite get to talk about histograms involving our CDF. CDF, again, stands for your cumulative distribution function. And what it does, it starts at, in this case with our binomials, x equals 0, and then adds up all those probabilities to whatever point you would like to get to, and so on and so forth. So for instance, in this one, this is the probability that x equals 0, 1, 2, 3. So this bar right here includes the probability that we have a situation where we have 0 successes, 1 success. Here it's 0, 1, 2, 3, 4. Okay, and so one of the things that always happens with a cumulative distribution function, we always end up 1, therefore we are always going to have distributions that are skewed to the left. All right, now we can also find the mean and the standard deviation for a binomial distribution. Mean makes sense. And again, notice some of the notation. Mu sub x, mu of my random variable x is n times p. Number of observations times probability of success. If you think about it, if I flip a coin 10 times, how many times would you expect tails to show up? And you would say 5, because you expect half of them, because that's the probability. That's the idea of your mean here. Your standard deviation, simply the square root of n times p times 1 minus p, or my mean times the probability of failure. Now, key thing, only for binomial. And so if I'm going to use these, I have to first verify that I do have a binomial distribution. Okay? Now, if you really are concerned about where they come from, in the book they do show how these formulas are derived. Again, these are going to be in your formula packet for the AP test, so you'll see those used quite often. All right, something that's not in our book. It says we describe the probability distribution of a random binomial random variable just like any other one, by looking at shape, center, and its spread, and if there were any outliers. Okay, and generally we won't have that situation. So when we go to that probability distribution that we've been using as an example, that family of 5 children, again, probability that none have type O bloods at 0.2373 and so on and so forth. And so here's our histogram. Okay, still talk about shape. Okay, we talk about it being skewed to the right. And what we would probably also want to add in here is that it's unimodal at x equals 1. We would talk about the center. In terms of our median, what we want to kind of look at is where would be the 50% piece, if we wanted to look at that. So you got about 24% here. So again, your 50th percentile would be somewhere, or your 50, your middle piece, your median would be about there. We could, if we had the data, calculate out my mean. Okay. Your spread, again, we want to talk about either my variance, my standard deviation, or we could even talk about the range. Okay, so we will get into that and how it's affected when we are transforming it and such. All right, suppose, this is another situation, suppose 10% of CDs have a defective copy protection schemes that can harm computers. Music distributor inspects 10 CDs from a simple random sample, 10 CDs from a shipment of 10,000. Let X be the number of defective CDs. What's the probability X equals 0? Okay, this is not quite a binomial setting, and why? Okay, now the why is that the probability that your first one is defective is 10 out of those 10,000. Now, probably your second's defective depends on the first. Okay? If your first was defective, now there's 9 out of 9,999. If not, then there's 10 out of 9,999. Okay? So it's not quite a binomial setting because my probabilities changed, but the probabilities are so very close that we're going to be able to use some of these properties of binomial distribution anyway. So here's what they talk about. They bring it in. Okay. Actual probabilities, known effectives, and what they did is they took 9,000. That's your first one, not being effective, all the way down. Okay, they drew out. It looks like quite a few, but I won't even worry about that. I would use my binomial distribution. 10, choose 0. Probability is defective, I want 0. Not defective, I want 10. So the probability that there are no defectives is about 35%. Now, what we're getting at is not quite all that, how we do that problem stuff, but it's this idea right here. This is going to be one of our conditions that we use a lot, and we'll talk about as a 10% condition. In inference, we'll use this a lot of times. It says if my simple random sample of size n from a population of size capital N, we can use the binomial distribution to model count of successes as long as little n is less than or equal to 1/10 big N. Now, we'll make a little change here. I talk about it as little n, again, is your sample. We want that to be less than or equal to 1/10. Big N is my population. And I think if you multiply both sides by 10, sometimes it's a little easier. So I always tell people, think about 10 times my sample. Is that smaller than my population? So for instance, if I went to my stats class, 35 kids, and if I did a random sample of 5, 10 times that is 50. Okay, I wouldn't be able to use the binomial distribution because of the fact that 10 times my sample is bigger than my population. All right, as n gets larger, something interesting happens to the shape of your binomial distribution. Figures below show histograms of binomial distributions for different values of n and p. What do you know as n gets larger? Now, one of the things we should look at and recognize is that in every one of these cases, the probability of success stays 0.8. But as the sample size increases, notice we get less and less variability. Okay? Now, what they're saying is that we're choosing 10, okay, and we're looking at the proportion of those 10 that give me successes and so on and so forth. And so it's a little different. We'll get into that more and more. Now, what it's getting at is your normal approximation for a binomial distribution. It's going to get closer and closer to a normal distribution as my sample size increases. And we're going to look at that more and more as we get into sampling proportions and sample means. Okay, so suppose we've already shown that we have a binomial distribution with n trials, probability of success p. When it's large, well, what's large? Now there's no set value again. Okay. When it's large, usually we talk about our 10% rule. The distribution is approximately normal with the mean and standard deviation. Well, that's nothing new. And then as a rule of thumb, okay, this is something else we're going to use as we come in. This is more of our conditions. This is going to be called our normal condition. Again, we'll use this a lot of times when we're checking for inference. Rule of thumb, we'll use the normal approximation when n is so large that n times p is greater than or equal to 10. Okay, so up here, n times p is 8. It's not bigger than 10, so we couldn't use it here. Okay, n times p is 16, which is greater than 10. So we might be okay there. But then also we have to check this, n times 1 minus p, or n times probability of failure. So 20 times 0.4, not 0.4, 0.2, I'm sorry. Is 4, which is not greater than 10, so I couldn't use it here. Okay. Now, 50 times 0.8 is 40. 50 times 0.2 is 10. I could use it there. So this is what we'll talk about as my normal condition. Okay, so in other words, another way they talk about your expected number of successes and failures needs to be at least 10.